All right, welcome back. We are doing 2.5. Don't freak out. We skipped 2.2, 2.3, and 2.4. 2.5 has to do with introduction to logic. Introduction to logic. So as I said, it's not until chapter 4 that we start doing hardcore proofs with triangles and whatnot. But I want to introduce you just to the idea of logic and how we go over and organize our thoughts and how important it is to be thorough with explanations in math. So on this one right here, it says, prove the following with the given information and other facts that you can think of. You must justify everything you state in your reasoning process. Background information. You overhear your aunt talking about how she wants to go to Vancouver, Canada, but she does not know if she is allowed to. You do know that she does not, or that she does have a passport. Prove that she is legally allowed to go to Vancouver. Yes, I understand you could make this much more confusing. You could say, well, technically, right now, with the COVID-19 deal, you can't go to Canada. Please just help me out with this. Let's assume that the main thing that you need to have when you're going to Canada is that you need a passport, okay? Um, so let's go ahead and run through this. Now, how you would do it, this is one of my most favorite ways of doing proofs, and this is the way that we're going to be doing it for the most part. We are going to be using something called a two-column proof. What a two-column proof is you write down things and you write down how you know that's true. Reason, okay? So the first one would be Aunt wants to go to Vancouver, Canada. How do you know that? This is one of the best parts of doing proofs is that some things are just freebie points because you can write down given. Aunt wants to go to Vancouver, Canada. That is just given. Okay. What else do you know? You know you need a passport to go to a foreign country. How do you know that? U.S. law. What else do you know? Vancouver, Canada is outside the U.S. Well, how do I know that? Definition of U.S. borders. Okay. What else do you know now? Aunt needs a passport. Okay. And that could be something called the transitive property. Okay. What else do we know? Aunt has passport. How do we know that? Given. Okay. So therefore, what do we know? Aunt, and my handwriting, this is, sorry, white that out. Aunt can go to Vancouver, Canada. Needs a passport. And has a passport. Okay, I'm assuming you guys are freaking out saying, what in the world is Gallagher doing? What does this have anything to do with geometry? What does this have anything to do with math? The answer is nothing. It has nothing to do with math. But if I jump straight into a geometric proof or any kind of math proof, you guys would freak out because you didn't understand what I was talking about. All I did was I just put some random story into the format that we will be doing proofs. Okay. One way you do proofs is a 2-column proof. The other one is putting it into words. Let me show you how you would put this into words. You would say, it is given that my aunt wants to go to Canada. By US law, you need to have a passport to go to Canada, or you need to have a passport to go to a foreign country. By definition of US borders, Vancouver is outside the United States. By the transitive property, my aunt must have a passport. It is given that my aunt has a passport. Therefore, my aunt can go to Vancouver because she has needs and has a passport. So the thing in geometry and with all proofs is that you have to put a lot of things in here that you assume would be common sense, like this. Or this. Canada, Vancouver, Canada is outside the US. You would think that was duh. I already know that, but you have to put it down because it is a part of the proof. Basically, you pretend like you're explaining something to an alien who knows nothing. All right. Once again, we would be doing a lot, or we will be doing a lot of these 2-column proofs, but there's also something called a paragraph proof where you can go over and put all of this into a logical paragraph. All right, so once again, we'll be getting into math proofs. I just wanted to show you an example of the depth you need when you're doing a proof, as well as how to organize it, and also these little freebies. Keep forgetting you guys can't see my mouse. The freebies, the givens, and stuff like that. So let's go ahead and look at some of the things that you can use. Okay, the addition property, and it should be of equality. What the addition property of equality says is if A equals B, then A plus C equals B plus C. What that means is you can add a number to one side of an equation as long as you add it to the other. If you had x minus 2 equals 10, actually plus, no, minus, sorry. If we had x minus 2 equals 10, then you could go over and add 2 as long as you add 2 on the other side. That is what the addition property of equality says. Subtraction property of equality, I'm going to say of EQ. What that says is if A equals B, and we know that's true, then A minus C equals B minus C. AKA, you can subtract anything you want from one side as long as you subtract it from the other. If we had x plus 2 equals 10, I could subtract 2 from that side as long as I subtract 2 from that side. Multiplication property says, and that should be of equality as well, if A equals B, then A times C equals B times C. Also known as, you can multiply one side of an equation by anything you want as long as you multiply the other one. If we had x over 2 equals 10, I can multiply that side by 2 as long as I multiply that side by 2. Okay. Now this one is the funniest one, I think, of the bunch. What this one says, the reflexive property says that AB equals AB. Anything is going to equal itself. Anything is going to be congruent to itself. Seems really silly. You will see in just a second why that is useful. Not really in a second, but in a little while you'll see why that's useful. Reflexive, okay? You can think of that as the reflective property. You look in the mirror and you see yourself. AB looked in the mirror, saw itself. AB, the segment, rather than the length, looks in the mirror, sees itself. Okay, so here are some of the different properties that we're going to be using. Addition property of equality, subtraction property of equality, multiplication property of equality, and reflexive property of equality. All right, next page. Okay, so on this one, make my pen right size. All right, here we go. Symmetric property says if A equals B, then B equals A. It just means that you can switch an equation and it means the same thing. A equals B, then B equals A. If 2 plus 2 equals 4, then 4 equals 2 plus 2. You can switch an equation, the left for the right and the right for the left, and it stays equal. The transitive property says if A equals B and B equals C, then A equals C. Example, if $1 equals 10 dimes and 10 dimes equals 100 pennies, then what does $1 equal? 100 pennies. Now, even though this is just A is to B and B is to C, so A is to C, this could be a longer chain. The way that I remember this is transitive is kind of like transitive. A is connected to B on a train. B is connected to C on a train. So what is true? A is connected to C on a train. Transitive, transitive. So we'll use that property sometimes too. Substitution just says if A equals B, then anywhere I have A, I can write B. For example, if $1 equals 4 quarters, I can walk over to your desk, take away $1, put 4 quarters, and you cannot get me arrested for stealing. Okay? Might be annoying, but I didn't steal any value. And then the last one, distributive property, is just multiplication across addition. You know what the distributive property says. That's the distributive property. Okay, so let's go ahead. Name the property that justifies each one of these things. How can I get from this step to that step? What did I do? Well, I subtracted 1 and I subtracted 1, so it must be the subtraction property of equality. You cannot just say subtraction. That just means you've subtracted. This means you're doing it on both sides. That's why we have to have of equality. This one, how did I get from this step to this step? Well, I divided. Did I divide on both sides? Yep. So this one would be the division prop of equality. Alrighty. Now the next one. What's this one? Distributive. Distributive property. Of equality? Nope, just distributive property. What is this one? I knew that x equals -2, and I also knew that, and then somehow the x went away and a -2 went where it used to be. What did I do? I erased the x and I put it in a -2 because I knew x equals -2. Oh, that one is substitution. So in math, a lot of times we want to go over and be able to explain why we're able to do something. How do we know that AB is congruent to AB? Well, AB looked in the mirror and saw its reflection. So reflexive, not reflective, reflexive. Now on this one, how do I go from that step to that step? I multiply by 2 and I multiply by 2, so it is the multiplication prop of equality. So I'm baby stepping you into these proofs. Yes, I know you can do this stuff without the proof, but I'm trying to show you easy examples where you're justifying steps and it's something easy that you're already comfortable with. Let's make this 4 equals x. So if I wanted to get from here and show that that's true, step 1 is just 2x plus 1 equals 9. How do I know that? It's given. Now what would I do if I was solving this? I'd subtract 1 and I'd subtract 1, so I'd get 2x equals 8. And why was I allowed to do that? What's the rule that allows it? Subtraction prop of equality. Now how do I get rid of this 2? I divide it away and I end up with x equals 4. That's the division prop of equality. Now lastly, I just did this so that we could have one extra step. I need to get to 4 equals x. I had x equals 4. Now 4 equals x because of, look back in your notes, which one allows you to switch left for the right and the right for the left? Symmetric prop. All right, so this is just us doing a basic little algebra 2-step equation, but justifying every step, explaining why we are allowed to do it for every single step. Obviously, this is not a real hardcore proof, but I needed to start somewhere. This is a baby step. Here's your little baby foot. Baby step. Okay, so baby step to go over and explain how to do a 2-column proof. All right, let's get into the big boy stuff then. Let's see. Okay, here's the big boy stuff. There we go. Okay, so if we're looking at this, this is an example of a real geometry proof. If we knew that the measure of 1 equals 3, then prove that AEC, this one, equals this one. Well, this should make sense because let's say this was 20 degrees and this was 20 degrees. It doesn't matter what this one is. Let's say it was 50. I understand that that's not to scale, but if you're adding, if this one is congruent to this one and you're adding the same thing both times, then the resulting angle must be congruent. So that's all that's saying. If you know that the first two angles are congruent and you're adding the same thing, then obviously the resulting angle will be congruent. So let me show you how we do that. How do we know that 1 is equal to 3? Well, it is given. You just got yourself 1 out of 5 points for that proof. Next, how do I know that 2 is equal to 2? Which one was the one where something can equal itself? Reflexive prop. Now, why am I allowed to just add a 2 to the left as long as I add it to the right? You might have absolutely no idea how to do this on your own, and that's fine. The level we're at right now is just explaining the steps that are listed. So why am I allowed to add the 2 over here if I add the 2 over here? Was there something that said you can add anything to one side as long as you add it to the other? Yep, the addition property of equality. Now, how do I know that 1 plus 2 is that angle and 3 plus 2 is that angle? This is not one we have talked about for a long time. What is the thing that says you can have a part of an angle and another part and it equals the whole? Part plus part equals whole. That is the angle addition postulate. Now this last one, we know that 1 plus 2 equals 3 plus 2. Here's where there was a 1 plus 2. We knew that equaled this. They erased this and put in what 1 plus 2 is. That's how they got that. They erase that one and take what 3 plus 2 was and put it in there. What was it called where you can erase something and put in what it equals? Substitution. That was hard. Do I expect you to be able to write this whole thing out on your own if it was completely blank? Absolutely not. We're doing baby steps. The baby step is I fill out half, you fill out the other half. You just need to be able to look at what's happening and figure out if it's reflexive property, substitution, what is it? Ask what happened to be able to get to that step. What happened to get to whatever step you're on? So let's go ahead and look at another one. Let's say we were here. Now I'm going to give the reasons, and you guys are going to give the two-column proof, the statement part. So what's the first given? AB is congruent to CD. I want to really quickly, before we jump into this is just like the last one. It says if that one was congruent to that one, and this was just shared, then this whole piece must equal this, because the original two were congruent, and then you're adding the same thing. Okay, so we know that this is congruent to that because it's given. Great. What's the reflexive property? What is the thing we want to say is congruent to itself? Well, in the problem above that, it was the angle in the middle. So what do you think this is going to be if we're doing the same thing but with segments? The segment in the middle. Okay, the addition property of equality. The addition property of equality is going to say that, dang it, AB plus BC must equal CD plus BC. All we did was say that when we had that, let's go ahead and add a BC to both sides, addition postulate. Segment addition postulate is going to say that AC is going to equal AB plus BC, and the BD is going to equal BC plus CD. All I'm saying is that this whole thing is made of its two parts together, and that's made of its two parts together. Now, once again, we know that where there is an AB plus BC, I can write what it equals. So I'm going to scribble that. I'm going to have this being the AC, and over here, I can scribble that out and put what it equals. BD. All right. Once again, another one I wouldn't expect you to be able to do on your own, but if you know what they're telling you is happening, then you have to make a guess. This one was harder than the last one. Okay, let's finish this puppy up. Let's say we had this proof right here. Fill in the missing parts. That and that are complementary. Proof that 10 or x equals 10. They are complementary. How do we know that? It's given. How do we know that they add together to be 90 degrees? Oh, that's just because of definition of complementary. I'm winging some of these. Okay, some of them we haven't written down in our notes, but we know that if two angles are complementary, then they add together to be 90 degrees. Their measures do. Next, how do I know that this is true? Well, one thing I forgot to put in here was that this one was x and this one was 6x plus 20. So, sorry, that was supposed to be written in the given. So that one would be, I erased what the angle was, and I put in what that angle was. What is it called where you can erase it and put something in? Substitution. Sorry for forgetting to write that. Next, what are we going to be doing here? We combined like terms, right? Then it looks like they subtracted on both sides, so subtraction, prop of equality. And then what did they do? Looks like they divided on both sides, so division, prop of equality. All right, recap on what we're doing here. These are hard. More than anything, I want to make sure that you guys are able to understand that we have certain justifications. We have certain justifications for steps we are going to do in proofs. If we subtract something on both sides, then that would be subtraction property of equality. If we divide on by something on both sides, division property. So in math, or in our geometry class, we are going to be explaining a process, and we're going to do steps, and we're going to explain why we're able to do the steps, statements and reasons why we can do it. So that's the most important thing. All right, I hope that made sense. We're starting to play with the big boys here. We're looking at logic and proofs. Stick with me. Come to office hours or ask questions if you have them. Thanks for watching.